let me see. Yeah, okay. Okay, I'll start explaining everything. So welcome everybody. This is New York Institute of Technology, School of Architecture and Design. MS, yeah, okay. Sorry, 1 second. Okay, MS in Architecture Computational Technologies. I'm Pablo Lorenzo Iroa, and I'm the director of the program. We had some feedback. I just put that the other video on pause. But today we are presenting a lecture from the spring 2022 semester lecture series, Pablo Moyano Fernandez. And I'm going to proceed to do a more formal introduction of the series and of Pablo's lecture and Pablo's biography. The Master of Science in Architecture and Computational Technology is a new program at NYIT, and the lecture series aims at looking at the relationship between information flows and robotic fabrication. The lecture series this semester is called Inform Actualizations from Artificial Intelligence to Physical Computation. And the MS lecture series aims at discussing research framed by invited guest speakers. The MS program focuses on architecture, expanding the relationship between science, technology, and cultures through innovation in algorithms, simulation, AI, robotic fabrication, and materials. The spring 2022 lecture series discusses alternative means to understand the dialectics between the ideal digital and the physical digital. Within an architecture of information, AI, robotics, and materials are thought as actualization interfaces. This process understands information flows and their actualizations as architecture. Pablo Moyano Fernandez is today invited guest lecturer and is an assistant professor in architecture at the Sam Fox School of Design and Visual Arts at the School of Architecture at Washington University in St. Louis. The lecture title is Sequential Casting Concrete Systems, and the lecture description is as follows. Historically, load-bearing masonry has served as the most fundamental substantial structural system for secular and religious buildings until the 19th century. However, in contemporary architecture, the separation of structural frames from non-structural enclosures became the predominant trend. Today, most building envelopes rely on exterior cladding systems that are independent of the structure. With the current advances in material technologies and fabrication, it is possible to challenge the traditional concrete formwork practices by hybridizing vernacular casting techniques with innovative methods. As a result, the construction of concrete load-bearing walls with variable cross-sections and non-conventional geometries can be achieved. Sequential casting concrete system is a casting method that offers a wide range of complex geometry walls while incorporating the latest concrete technologies. Concrete's reliance on formwork due to its unique property of state changing from fluid into a solid brings mold making at the forefront of concrete's possibilities. Pablo Moyano Fernandez, an assistant professor at Washington University in St. Louis, who has been teaching since 2005. He holds a professional degree in architecture from the University of Buenos Aires, a Master of Architecture and Master in Urban Planning Design from Washington University. Pablo has extensive experience in the field of architecture, developing his career in firms with a strong connection to construction. His teaching and research focus on the performative qualities of concrete applied to building enclosure systems using innovative method of fabrication coupled with novel types of concrete. He has been awarded numerous research and teaching grants for his work. He's the coordinator of Building Systems, a foundational course that examines contemporary building practices. Pablo served as Team WashU's University Project Design Leader for the design and construction of Crete House Solar Decathlon 2017, which was awarded the second place in the competition architecture category contest. For more information, performativeconcretehub.com. Thank you, Pablo, for being with us. Pablo has been a colleague of mine in the University of Buenos Aires, so I'm very happy and honored that Pablo is here sharing his experience with us. Just a little bit about the lecture description. I could not agree more with the separation between cladding, facade system, and structural system. Is something that actually is fundamental in our course, right? So I'm very happy to have your presentation today, Pablo. because we're actually looking at that separation as a problem. We usually name the case of the few architects in New York City that actually avoid cladding, and there are like very few buildings. You can count them with 5 fingers of your hand, by the way, right? Because they most of the time there is a separation between the cladding system and the structural system. They are not totally related. So I'm very happy to have you here in our lecture today. We'll discuss that later, but thank you for being with us, and the floor is yours.
Great. Well, thank you, Pablo, for such a long introduction. Well, I'm very happy to be here. I'm very excited to share my work. Well, as Pablo already mentioned, I am very fascinated by concrete. It's the focus of my research. Well, the idea of this lecture is to show you, I know we're limited in time, so I'm going to show you what I've been working on during the last year. So it's only one actually research project, but has multiple, in my opinion, multiple applications. Hopefully you guys enjoy the presentation. I would like to start by what you see on the screen is the Performatory Concrete Hub. This is actually a website that I recently developed, and it's basically a platform that consolidates my teaching and my research. It's a dissemination tool that basically showcases applications and possibilities of concrete as a versatile construction material in experimental but also real projects. So the matrix that you see on the screen is actually represents the inextricable connection between my research, my practice, and my teaching. In the last century, building technology has witnessed increased level of innovation in materials and assembly methods. With the emergence of digital fabrication technologies, architecture as a discipline, but I would say the whole construction industry in general, has greatly broadened its options in terms of the materialization of building assemblies. So the availability of a robust digital platform provides designers with a new set of tools that can enhance their creativity and potentially increase the complexity of building components. All this is really exciting. Now, while digital fabrication tools can offer appealing construction methods, those methods usually rely on labor-intensive processes to set up the equipment, to assemble components, and finish the final pieces. Consequently, there is usually a wide gap between assemblage process required by digital technologies and the methodologies effectively adopted by the building industry. However, in the case of concrete, there is fertile ground for exploration in terms of digital technologies applicable to formwork making, and of course, its impact on casting methods. Concrete reliance on formwork due to the unique property of state change material from fluid to a solid brings the idea of a mold really at the forefront of the possibilities that this material offers. And this is precisely where my focus of my research is. So I have been testing methods to integrate new technologies into the production of formwork making techniques. I am particularly interested in exploring the performative qualities of concrete in building envelope systems using innovative methods of fabrication connected to also material innovation, in particular in concrete. Concrete, as we all know, is a widespread material worldwide. It is used in countless applications and is specifically prominent in building structures and infrastructure projects such as highways, bridges, many other large-scale projects. Now, concrete intrinsic properties, when they are coupled with new advancement in material capabilities, has increasingly enabled the use of that material into building envelopes. Concrete is considered by some historians one of the oldest building materials. As you know, it was frequently used by Romans many, many years ago. So the Dome of the Pantheon, built actually more than 2,000 years ago, is an eloquent testimony of the architectural possibilities, as well as a reliable evidence of the longevity and strength of the material. However, somehow after the fall of the Roman Empire, the material virtually vanished. Two French theorists, Rondelet and Bourgain, in their construction treatises in the early 1800s, describe the methods used by the Romans and question why modern architects would somehow neglected the use of such a cheap and efficient system like concrete offered back then. When concrete came back into use as a building material, it evolved from a rather humble origin called the Pissé construction. Although the use of mud dates back from the original civilizations, the technique was extensively used in Spain since Roman times, but also in France in the Lyon area in the 1700s. The system consisted of ramming packed earth between movable formwork. The formwork consisted of parallel set of boards which slide between vertical posts. So the boards were raised once the earth was compacted and the process repeated. Ram earth is one of the oldest construction techniques done by civilization. Making ram earth involves compacting a damp mixture of soil with suitable proportions of sand, gravel, clay, and some stabilizers into a formwork. Historically, additives such as lime or even animal blood were used to stabilize the mix and make it more cohesive. By using local materials, building can establish a strong connection with their environment, in addition to minimize transportation and the use of outside resources. The importance of Pissé in the development of concrete construction lay not so much in the material use, but most importantly in the technique. The peculiarity of Pissé construction is based not only in the economy of using earth as a building material, but in the process by which a building is literally molded into its final shape. So this very primitive construction method had revolutionary implications in the future of concrete as a building materials, as we will see. Thomas Edison, as you probably all know, was an American inventor, but he was also a businessman. He developed many devices in fields such as electric power generation, mass communication, sound recording, motion picture, and many more. So these inventions, which include the phonograph, the motion picture camera, and early versions of the light bulb, have, as you know, widespread impact in the modern industrialized world. But behind all these successes, there have been also some failures. So in 1908, Edison filed a patent about a home that could be built using a single pour of concrete, single cast. So Edison had prior ventures in concrete, so he was very familiar with the material, including a cement plant in New Jersey, near where you guys are. And he had patented several improvements using concrete. So in 1917, he actually got a patent that, as you see on the screen, basically consisted of basically building the entire mold of the entire house, and in a single cast, really build everything. Everything means foundations, walls, floors, ceilings, even staircases, even partitions, bathtubs. Everything was cast in a single cast to make the entire house. So according to him, this building will be fireproof, insect-proof, of course, easy to clean, very quickly to build. Now, however, even though the system didn't quite work, it has some problems. He actually built a few houses. Some of them are still standing today. But to me, it shows a very interesting precedent that intends to take advantage of the fluid state of the material into something that then becomes very robust. So that was kind of the inspiration here. So the Pissé system evolved through time. The most obvious improvement was the increase of cohesion between earth and mixing with a stronger binder. And many experiments were done, but ultimately that led to the modern concrete. Francois Cointreau was a French architect. He was one of the first ones to use the system more extensively in chapels and other buildings in the Lyon area. The latest version of this technique is called slip form, also called jump form. This is a method of construction in which concrete is poured into the top of a continuously moving formwork. As the concrete is poured, the formwork is raised vertically at a speed which allows the concrete to cure before it is free from the formwork below. This is the fastest method of construction today for reinforced concrete structures. However, it is economical only for tall buildings. We're talking about 10 to or higher, right? 10 stories or higher. It's very common in building cores, bridges, silos, water towers, and very, very large scale projects. But it's not really feasible for small scale structures, primarily because the high setup initial cost. The system can also be used horizontally, like highways. You've probably seen this when you drive around, but also in bridges, also incline, even taper structures can be built this way. And even complex geometries can also be achieved using the same system. Now, concrete has inspired a number of artists and designers across the world. Rachel Whitered is a very prominent British sculptor of her generation. She actually cast the spaces inside and around objects. The resulting sculptures are remarkably faithful to the source of them all, but also strangely foreign because they represent the inverse of the original. In her work, absence is made present, interior becomes exterior, and the invisible becomes visible. Her project house, which is the image on the left, was a large concrete cast inside of an existing Victorian house near in the vicinity of London. And then basically what she did is she took a house set to be demolished, asked permission to local authorities, and she cast concrete inside the entire house. So basically she used the house as a mold and then took it out, and then you get what you see on the screen, the left image, you get the opposite. It's interesting because it's exactly the opposite of Edison's approach, right? So instead of casting the house, she's casting inside the house and get the opposite. So walk-in assemblies, the image on the center by Maror Design, by Brandon Clifford and others, they were inspired by mysterious knowledge surrounding the transportation and placement of megalithic structures in the past. So the image you see there on the screen is basically big components made out of their large piece of concrete called massive masonry units. And so these units become performative sculptures. It's very interesting because by using variable density concrete and then calculating very carefully the center of gravity, they can very precisely move these with very, very little effort. So these are, several thousand pounds heavy, but they can be easily moved by a single person. There's actually a video you can find online, very, very interesting. Crash wall, the image on the right by Walter Jack, is an expansive 40-meter long high wall, 40-meter long, but also 3-meter high wall. The project is about geology because it's a retaining wall, but it's also about process. So the artist, Walter Jack, is interested in how things are made. So we typically register concrete as a hard material, and it's typically not noted for the fluidity and softness, right, of the material. And yet concrete is a liquid. So here the intention is to retain the liquidness of its process. So for the last year, as I mentioned, I have been working on the sequential casting concrete. So this is a construction method that was inspired by the two conditions that I just described. On the one hand, the unique state change property of concrete from fluid to a solid, but also the idea of a formwork, right? So the idea of formwork not necessarily as a static entity, but as a dynamic entity. So that's where my research is interested in. It really challenge the conventional mold making, and then trying to produce, in this case, load-bearing building enclosures. In order to explain this, I'm going to quickly revisit how the wall as an architectural element has evolved over time. Historically, bearing walls have been the primary structural components for buildings. During the Neolithic age, the construction of shelters experienced a radical shift from large animal bones into load-bearing masonry employing manufactured materials such as paddle mud or mud bricks. Load-bearing masonry continued to serve as the most fundamental and substantial structural element for secular and religious buildings until the 19th century. However, in contemporary architecture, the separation of structural frames from non-structural enclosures became the predominant trend. Today, most building envelopes rely on client systems such as rain screen, curtain walls, or even barrier systems that are completely independent from the structure. On the other hand, building structures during the 20th century responded primarily to rectilinear industrialized products such as steel sections, lumber, and plywood. Therefore, contemporary load-bearing walls are usually single flat vertical surfaces made primarily of masonry, bricks or CMU, wood or concrete. Those are the main materials for load-bearing walls. Sequential casting concrete system is a proposed casting methodology based, as I mentioned earlier, on slip forming, but the system hybridizes vernacular methods of adobe construction with cutting-edge technologies and materials. It delivers low-bearing enclosures that integrate structure and skin that can include highly customizable geometries that are simple to fabricate by non-skilled labor. They're also efficient and resilient. So the proposed system somehow fits right in between ancient construction techniques and modern client system, capitalizing on the advantages of load-bearing wall assemblies. The system offers highly articulated profiles that allow complex geometries, including a wide range of finishes, textures, while incorporating the latest concrete technologies. By using ultra-high performance concrete, this is a fairly new material. It was developed in the last decade and a half. The system provides durable concrete structures that rely on the use of a series of small and economic molds, which can be either handmade or 3D printed. It is simple and can be executed by unskilled labor. The sequential casting system capitalizes on the plasticity of ultra-high performance concrete to produce intricate geometries, and its very high compressive and tensile strength allows a drastic reduction of the overall thickness, but also material usage and actual weight of the structure. As a result, the wall is free from limitation in its geometry and materialization using a simple, low-bearing, low-cost concrete construction system. As a proof of concept, I built 8 mock-ups that were fabricated using most of them standard desktop 3D printers for the molds, but also some conventional wood frame made with interchangeable urethane rubber inserts. So the work was partially funded by a creative activity research grant by Washington University, and it has been condensed into a paper called Sequential Casting Concrete Systems in Low-Bearing Concrete Enclosures that was published last year in the Advanced Building Skills Conference proceedings as part of the session New Forms of Concrete in Bern, Switzerland. So I'm going to show you now some of the mock-ups that I just made, some drawings that showcase how the system works. So this is the simplest one. As you can see on the right, it's just a flat wall. The way that it was made is using, as you can see probably in the center of the drawing, it was built with using these plywood frames. Then rubber insert is placed in between, and then basically you create rows, and then you cast the concrete sequentially. I'm going to introduce first some of the prototypes, and then I will go in more detail how it's built. Since the system consisted of small-scale molds, is it possible to incorporate gradual shifts by displacing the units to produce an irregular layout? So this offers a possibility of constructing relatively complex bearing walls with articulated surfaces. So in this case, as you can see, the thickness of the wall is kind of the limitation of the shift. The thicker the wall, the more shifts you can create, but definitely the system allows for that. As you can see on the top section also, the system allows tapering walls, so you can actually decide the thickness of the wall as you go up. In this case, I'm following gravity, so basically making it thicker at the bottom and thinner at the top, but that can be, of course, challenged and can be changed. In this case, I'm using the same wood frames, but changing the urethane rubber molds from a flat one to one that is pixelated. So, and then that mold, I have 5 of them, 5 different pixelations. And then by rotating them and mixing them as you go up, you can build a fairly micro-articulated surface. In this case, the inserts were done with 3D print molds. Basically, each of the molds that you see there are 4 by 4 inches, are fairly small. So I use always only desktop 3D printers, very cheap. You can buy one for $200 or less. So the whole idea of the system is to make it available as much as possible. So anybody can actually, that can access to a 3D printer can actually build this. And then the wood frames, of course, can be done by anybody that's familiar with using wood. In this case, I created like a gradient. So of course you can change the arrangement of the units, but the idea of grooving can provide not just aesthetic to the wall, but also potentially can be a self-shading device to create basically a surface that is that serves as a geometric actuator for thermal flows. So you can actually carefully, based on the orientation and the place where you are, you can carefully design a system that is more efficient in terms of solar radiation control. The system allows also for integration of other materials, so it doesn't have to look like concrete. In this case, I'm adding bricks. I'm going to explain this a little better later, but this is not something that, this is something common in the precast industry. They actually use what's called face bricks. So they lay them down into a form liner, and then they cast concrete in a flat bed, and then they tilt it up, and then you have the wall with bricks. So it's a technique that is used in the precast industry. But in this case, what I'm proposing is use recycled bricks. So you can actually cut them very easily with a tile cutter and then create these kind of structures. I'm going to explain this a little bit better in a couple of slides. The system also allows for permeable walls. So in this case, this is inspired by the half-tone reprographic technique, which is basically a matrix of dots with different sizes and spacing, which allows monochromatic printers to simulate tonal variation from a photograph or an image. So that's a kind of old technique today. That's how the newspapers used to be print based on. But inspiring that system, I created 7 different molds with a pin, as you can see in the center. The pins vary in size from 1/2 inch diameter all the way to 3.5 inches diameter. So then you can pick and choose different arrangements to create actual images. In this case, it's a fairly small mock-up, so I only did like a gradient, but in a larger wall, you can create much more interesting images. This one is inspired in a game that I saw. It's called the Canoodle. It's basically a game that consists of little balls connected, forming different pre-assembled shapes. And then I used to fill predetermined areas of a board. So in this case, by using the system, you only have 6 different molds. You can rearrange them in different ways, and you can create this maze-like configuration. So not only the wall can be permeable like this one with through holes, or they can be solid. So it depends on how you make the mold. But the idea of acoustic properties, I think, is kind of emerged from this type of mold. And the last one is the what I call undulated. In this case, I'm only using 3D printed molds and no frames. So, and it's only 3 different radiuses and then some flat pieces. And with just simple variation, you can create highly articulated walls that, of course, are load bearing, but also very thin and very, very strong. So a little bit about, I'm going to show in more detail a couple of the options. So one thing that I'm very, very interested in about the system is the application in low income and low resources communities. So the first test that I made was this one, using, as you can see on the screen, literally I use milk containers to create the molds. So basically, I took the bottom of the milk container, which are roughly 4 by 4 inches, and then use the remaining part of the container to do like a second layer in order to make it a little stiffer and stronger, and then create these little boxes. They are very, of course, simple to do. Now, what is interesting about this is because it's a milk container, So the material is, of course, impermeable. So the hydrophobic nature of the material works very well in contact with wet concrete. So it allows a very easy mold release while supporting multiple casts with no deterioration of the mold. I'm using also very cheap clamps. You can buy them online or in a store for less than $1 a piece. One thing about the system is because it's done sequentially, as you can see on the screen, so you can have to do layer by layer. So because of that, you can actually use very cheap and not super strong clamp because the amount of concrete that you pour is only, in this case, 4 inches tall. So it's not a lot of pressure. So the hydrostatic pressure is usually a problem in formwork for concrete. You need very strong molds. But in this case, because it's done sequentially, the pressure is much, much lower. So with simple clamps, you can actually make the system work. Well, and then, of course, as you can see, this you can keep going up. I mentioned earlier, as you can see on the left, the thickness of the wall can be changed, can be tapered, or can be also vary all the time, depending on the design. And then, well, as you can see there, you can create these kind of articulated walls. Concrete is a material that has already excellent acoustic properties that mitigates reverberation of the sound waves. If on top of that, we shape it into a certain geometries, we can create walls that are very effective noise buffers. And that's what I did with this prototype. So in this case, what I did is create the molds that you see on the left, CNC from a CNC machine that we have here. And then I paint those molds, sand them very well, and then cast rubber. I use that rubber, as you see on the middle and on the right, use that rubber mold for the formwork. The rubber is urethane rubber, is very strong. You can do literally thousands of casts without deterioration of the mold. So this is super strong and super, it can be used many, many, many times. To obtain the voice, in this case, of course, you have these inserts in the rubber, and then you can create actual full penetrations. That, of course, you can decide not to do that and have a solid wall as opposed to a permeable one. But in this case, I just did it with the permeable option. And then, as you can see in the section, is you have all those voids. The one important thing about everything that I'm showing you right now is the concrete type that I use. So this is not conventional concrete. I'm using ultra high performance concrete. This particular material has the properties of being 5 to 6 times stronger in compression than traditional concrete. To give an idea, traditional concrete is around 4,000, 5,000 PSI, means 5,000 pounds per square inch. That's how much pressure they can resist to compression. The material that I'm using is around 20,000 to 25,000 PSI. So it's 4 to 5 times stronger to compressive strength. And it also has much, much higher tensile strength, which concrete, you know, is not very strong in tension. This material, because I'm also adding some fibers, it also has very high tensile properties. Not only that, but also the way this material works, I'm using special plasticizers to make the mix much more fluid. So therefore, allows for fairly complex molds like this one to be filled in a single cast without vibration at all. So I'm not vibrating anything. I'm just casting. It almost looks like a pancake mix. It's super, super liquid. You can literally pour it into the mold, and then it's self-consolidating. It completely fills all the gaps, and you can create fairly complex shapes without need of vibration. This one, as I mentioned earlier, is only done with 3D printed molds, as you can see, following, I created a series of curves and straight pieces. The system also is very important that allows reinforcing. So as you can see, all the mockups that I made has steel rebars on it. So that way you can create a system that is truly load bearing. So can have structural properties. So in this case, this example that you see on the screen is only 2 inches thick. It could have been done. I could have done that even thinner because it was the first one. I wanted to be a little safe and make it a little thicker. But The material allows for a drastic reduction of the thickness, maintaining the structural integrity. And well, that's why you see all the reinforcing. In this case, I'm using white cement, so you get a white wall, but can be done with traditional gray. As you can see here, you have three, well, in this case, 4 different strips, but 3 different curves I use to get those curves. And this one is the one that with bricks. So the idea of this one is, again, as I mentioned earlier, is to use recycled bricks that can be a debris or any leftover from older buildings or demolitions. What I'm proposing is, in this case, is with a tile cutter, which is not a super expensive tool. You can cut the brick very easily. It's very big. It's fairly soft material. In this case, what I'm doing is I'm creating these rubber form liners that have these grooves. So the pieces of brick can be inserted into these rubber molds and then hold in place, and then you cast the concrete. As you can see on this image, so I'm showing on the left only one side, but on the right you see both sides. So you can hold the bricks in place with these form liners and then cast the concrete. You can also, of course, reinforce, and then you can create a very strong structure that also has all these brick face. I'm creating this pattern, again, like a gradient, but you can, of course, do any pattern you like. You can use different color bricks. You can use also other materials, not just brick. But this is just showing brick as a more traditional way of masonry construction. And just to finish, I'm going to show you just one project that I just finished developing. It's not built, but I plan to build that this summer. So this wall system that I'm showing here is called operative walls. It utilizes the sequential casting concrete system principles applied to, in this case, a real intervention in a residential backyard in San Luis, here where I am. So it combines the undulated prototype with the face brick prototype that we just seen in the prior slides. So I basically am proposing 5 segmented walls that replace an existing wooden fence. These walls provide an active enclosure and a physical boundary for safety and privacy. But the walls, as you can see, are designed with a geometry that can result in a series of canopies, protecting from the weather while activating the surface with different uses. For example, a bench, herb planter, a countertop surface, also storage. And even on the right, you can see an integrated grill system called parrilla in Argentina, the country where I'm from, very, very common. So the idea is to incorporate that into the wall. So you can, and then it has a chimney, so you can properly basically burn coal, charcoal, or wood for cooking. Now, the idea in this case is mixing 2 materials, brick, but also slate, which is the predominant construction materials in the context of this project. So that way I establish a visual integration between the context and the proposed project. So, and then basically I'm using bricks, but also slate, or even can be asphalt shingles, which is a very, very common material here in San Luis. So it's cheap and it's very durable. So you can actually use asphalt shingles, in this case, combined with bricks to create that kind of visual integration. And then a couple of renderings showing how it would look like. So it's an alley, so it's not a very pretty street, but it's a condition there. So the idea is to face on the back with this, material that responds to the context, but on the inside of the courtyard, you create all these activities. And then, well, this is kind of showing the volume of that. So, okay, but if you are interested in learning more about this project or others, you can visit my website. It was just launched very recently. It shows not only the project that you saw today, but many others. Today, because of the length of the lecture, I only focus on one, but I participate in many other projects using concrete. But also in the website, you can see a lot of student work that I've been teaching for the last 10 years or more. Studios, but also seminars in which we use concrete as a construction material to build not just building envelopes, but also furniture, even pavers, and other applications. Okay, well, I'm happy to answer any questions that you guys may have.
Yeah, thank you, Pablo, for your contribution to our program and for lecturing with us. This is a very interesting presentation. Actually, you know, I've been working with what I find interesting about what you're doing is that it's not only that you're doing a casting concrete system, but to me, the interesting part, which is something that I've been working since I actually came to the US, because you know, the typical problem, not only in schools of architecture, but in the US in general, in relationship to architecture, is that every time there is a new machine, you have like all the architects just following that technology. That's happening, you know, with a robotic arm, with a 3D printer, right? Like, in other words, there is a and you know, my first declaration in terms of computation was the issue of authorship in relationship to software, right? Because software is in reality a package in which all the possibilities are already included in the programming of the software. And the same happens a little bit with machines. Of course, there is a lot of flexibility, but to me, the issue that you are raising is that if you want to innovate, you need to innovate at the level of the machinic system that produces the set of possibilities. And that's was one of the declarations when we did Acadia 2010, and the architecture information book actually declares that you don't only need to innovate in terms of aesthetics and, you know, all the usual problems that are being discussed in the US, but you need to also innovate at the back end parameters. And I think that that's what disruptive technology means, right? That you develop a system that basically changes the game. And I think that your machining system is actually operating, starting to operate at that level. We are actually, the program, this is a new program that we develop, and the idea is actually to develop information systems and to develop a robotic system for construction, right? That's one of the objectives because of what I'm just saying. Now, the question that I have in relationship to your machine, which, by the way, there are actually a lot of people work on that end, and so I'm very happy that you're working with that, is, you know, going back to the original, there are two questions that I have, maybe comments, right? Because the reason why I'm working with 3D printing with concrete, actually, and with other, you know, you mentioned different materials, which is very interesting. But one of the reasons why I'm still thinking that 3D printing is a little bit of a hope is the initial phrase that you put in your presentation, which I reacted to, which is the fact that when you use concrete, you are removing the cladding, right? Because you have enough, you know, thermal inertia, you have structural condition, right? That everything is built up into the modern idea of integrating everything into a fluid, one single fluid plastic material, which is what you said Thomas Edison figured out for the house, right? Now, the question, the reason why I'm still insisting with 3D printing, and the problem of 3D printing is the toothpaste, right? Like, that's why we're actually working with a toolpath to change that, you know, the toothpaste. The culture usually mentions the toothpaste because it looks like you're pressing the toothpaste and then everything is like a toolpath, right? And we're trying to break with that problem. But still the issue is, you remove the cladding, right? This is my problem with concrete. And I'm sure you're probably thinking about it, right? You remove the cladding, yes, fine. But in order to do the concrete, you originally did cladding, which is the foam casting problem. That's the typical problem of reinforced concrete, that you need basically to do the building 2 times, because you have to do the entire building as the foam work, and then you pour the material that you use, and then you remove. So there is no cladding. I totally agree. By the way, I'm mentioning Vignoli's building. You know, I don't know if you know the tower, the big tower that has a lot of problems, but it's the only skyscraper. Is the only skyscraper that doesn't have a cladding, right? And there are not that many in the world that do not have cladding, because the structure,
yes,
the entire structure is a slender building, has a lot of structural issues, and the envelope is the same thing. It's a continuous thing, like what you said. So, but the problem is that if you think about the removal of the cladding was literally there and was removed and taken away. So how are you thinking in terms of that problem? So that's like a long, your system raises a lot of questions. That's why I'm thinking in terms of a lot of items that we have been thinking about.
Yeah, I think you're making a very good point, a very important point. I can answer this in different ways. 3D printing concrete is of course a technology available today, which requires no formwork, right? So you just, as you said, toothpaste, you do walls.
My friends that do 3D printing are going to hate me again, but
no, but it's true. It's true.
Toothpaste, right?
I actually visit ETH Zurich. I went there 3 years ago. They are one of the high-end, top of the notch technologies that are developed in ETH. And they actually I talked to the Ena Joret. She's the one that did the dynamic casting. It's not 3D printing. It's a different system, but it's similar in a way that it's based on slip forming. But there's a lot of people researching right now at ETH doing 3D printing, and one of them was very, very interesting that I saw. It was in a phase developing. Is actually they were doing a 3D print mold that is disposable. So basically, they call it weak mold. So basically, they 3D print a mold, and at the same time they cast concrete, right? But then the mold is very weak. And the material is also recyclable, so almost disappears. So you throw it away, but that allows you to build in a slightly different way. But that's like a side comment. Going back to your point, Pablo, it's true that in the system I'm showing you is you have mold, but the big difference to me is traditional mold, right? You had huge panels, right, to build your cast entire floor, right? At least one floor. Otherwise, it's not competitive from a cost and time standpoint. But then most of that formwork, usually a big chunk of it is just thrown away, right? You can reuse a portion of it, but depending on the project. So in this case, I'm using very small molds. And on top of that, you need scaffolding, you need a lot of support, you need ties to connect the two sides together so it doesn't split and so on. This is fairly complex. The system I'm proposing, you only need 2 rows of molds, right? Arguably, depending on the design, and then you reuse those constantly. So you're not building an entire wall, a mold for an entire wall, you're building like a little portion of it, and then you reuse that constantly, right? So you're saving a lot of material. It is more time consuming, it's true, so it's not a perfect system, but it can be implemented in a way that for some projects, it may work, right? So you're reducing drastically. And by the way, in the construction industry, when you talk about concrete cost, about 60 to 70% of the cost is mold making. A big chunk of that is labor, but also materials. So the system I'm proposing is drastically reducing the labor, but also the material for formwork. So it's not necessarily a game changer, but I think contributes to a system that is much more efficient and using much less resources. But yeah, that's kind of one answer to your question.
I think that what I like about what you're doing is that independently, I know that there's always advantages and disadvantages. I'm not criticizing what you're doing, because I think that what's great with what you're doing, that you're thinking about the mechanic system. And actually, we're actually reviewing, it's basically your system is an analog computational model, right? Like the looming machine, right? Like it will, because you're programming it. The thing is that you're not automating the programming, right? Which is perhaps the missing component that you could add. I know that you're working there with Chandler, right? So it's there in the university. So I just wonder, or maybe we can think about doing one together. By the way, and think about collaboration between my program and what you're doing there, because the way that you're thinking, I like a lot. That you are addressing the fact that you need to think about the casting as a form of structure, right? That can be the machine that defines the parameters, right? That's what I think is the advantage of what you're proposing. And then, nobody actually, what I'm saying, nobody resolved it. So I'm not saying that, so you know what I mean? Like, I'm not pretending that you are going to resolve it. The one that you mentioned about the ETH, actually, they invited me for a lecture in 2015. I was there, and it's amazing what they're doing. And actually, we usually invite people here to talk. The one that you're saying about the disposable one, still you're making it twice. By phases, right?
Yeah, it's true.
It's still, but the sliding one that you're saying, the dynamic one, is
more dynamic casting. Yes.
And yours can become that because you could move it, right? Like
of course.
That's the idea, right?
But the thing is, what I'm proposing, Pablo, is I'm interested in, of course, digital technologies, but also latest technologies in concrete, like ultra high performance concrete. So by mixing those technologies, material technologies and digital technologies, you can potentially do a system that is more efficient in terms of reduction of material usage and so on. So for me, that's I'm not trying to. That's what I said earlier. I'm kind of in between vernacular, Adobe construction, very, very primitive, to something that is much more high end. Maybe I am right in between. So the idea of handmade portion of this or analog portion of this, to me, it is an issue, but it makes it available almost anywhere. That's kind of the goal, right? So anywhere in India, in Africa, in, I don't know, South America, wherever you are.
Hold on. In the US, we also have a lot of poverty, so we don't need to export. We are not going to save the world from the. We need to first solve the world in the United States, right?
Yeah, true. Yeah, absolutely.
No, I like that. Actually, I appreciate that about your project, that you're thinking in terms of sustainable. There are different types of sustainability, right? You're thinking about the social sustainability.
Right.
The other question is maybe the students. Do you have any questions, by the way? Because the other question to me is, that the reinforced concrete, of course, and I remember when you came to Cooper Union, we had this discussion with Elizabeth O'Donnell, right? I don't know if you remember.
Yeah.
That, in general, in the US, there is a lot of trees, which does not happen. We just had a lecture last week by Aaron Sprecher, that for instance, in Israel, there's no trees. There's no forest, right? So they rely on, they're actually doing a 3D printer that is based on the soil of the region, right? And in the US, you have a lot of trees. And I remember the discussion that we had about the sustainable factor of concrete. Did you advance in terms of that? Because I'm still defending concrete in some sense. I think that of course there is a problem of the preparation of the site, that the particles of cement, they spread while you are before you make it liquid, right?
Yeah.
So you have the problem of in the cantier, right? To actually develop cement also pollutes a lot. So did you think of any way of addressing that issue?
Well, I think that question comes a lot. I mean, sustainability of concrete is definitely an issue, but there's a myth also, I think, right? This is my opinion, but the problem with concrete is the cement. It's not concrete, right? So people blame concrete to be non-sustainable. And it's because the cement, to produce cement, you need a lot of energy, right? It's truth. So it takes a lot of energy to produce, actually take limestone, crush it, and then you need to grind it and then heat it up to high temperatures and then do the same process again. It's a long process and very energy consuming process. But if you think about a mix of concrete, right, only 10% of any concrete mix, or even less, sometimes 7%, can be up to 15 or more, but usually around 10% of the entire mix is cement. Everything else is fairly raw materials. It's actually gravel, sand, and then water, right? So that's the main components of 99% components of the concrete. So I would argue that only 10% of the concrete is really not very sustainable. But there is a problem here because people tend to compare a wood house, made a concrete house, and are much more sustainable. But it's important to think about the life cycle. This is very, very important.
The amount of energy that you need to heat up a house in the US is
exactly
control.
Yeah, not only that, but also the life cycle of the material, because typically the wood houses, we actually did when we did a sort of decathlon project, the house, we actually had a couple of students from engineering doing some analysis of carbon emissions and embodied energy. And they actually, what they calculate is typically a house in the US, a wood house, which is the predominant construction type, usually in the market lasts around 30, 35 years. That's kind of the lifespan of a house.
If you're lucky.
What's that?
If you're lucky, because
if you're lucky. No,
most of the time they last 10 years.
Exactly. Well, but exactly. But let's say 30 years is a mark, right? It's an average. Of course, some of them last longer, some of them last much shorter, but 30 years is kind of the target, right? In the market. Concrete houses, on the other hand, they can last 100 years. I saw the Pantheon today, right? 2,000 years, right? Yeah, still there. Done by the Romans 2,000 years ago and still there. So concrete, the longevity of the material is so much higher, so much longer, but also if you do it properly, have no maintenance. So if you think about it, right? Imagine a wood house and a concrete house. A concrete house is resilient to tornadoes, hurricanes, flooding, humidity, fire, insects, it's acoustically better, it has thermal mass. So it has so many, much more benefits than cons compared to wood construction. So, but also lasts much longer with no maintenance. So there's no required, for termites and all this fire and all this stuff. There's nothing they have to do about concrete, and it lasts again 3-4 times the time of a wood house. So they make this math, and they said the conclusion was in a 3-cycle period, 100 years. The amount of energy that you need to produce a concrete house versus 3 houses out of wood is about equal. I don't know, I don't have the numbers with me, but I can actually have a slide I can share with you. If you look at the concrete building, a concrete material, but then compared to a curtain wall building, for example, that's the predominant trend today, I spoke earlier, concrete has much less embodied energy than aluminum or even glass. Even bricks has more embodied energy than concrete. Than cement, not even concrete. So it's very relative. So it's really how much you use, how much does the building life cycle last, and then you have to compare apples to apples. And then I think I would argue that it's really sustainable because it's, for all the reasons I just mentioned.
So in a way, we have to, because I was wondering, all of a sudden, wood is very sustainable. And then you have a wood industry that's becoming very big, right? And what are the biases of one versus the other? The other problem of concrete is the runoff, right? Like when the water, right? When you're pouring concrete, then there is toxins, right? That they return to the ground and so on. But I would like to know more about it, because I also agree with you about the thermal. To me, the most difficult thing in the US in general is the thermal mass. Right. That the houses do not have thermal mass, and therefore it requires a lot of energy to cool and a lot of energy to to heat up, right? So the relationship between the two and the material and the cycles that you're referring to is very important.
Right.
Do you want to say?
Thank you for the presentation. This is not a question, but like I just think it's very interesting how throughout the presentation you kept highlighting the fact that your system can be easily made out of low-income material and thinking about recycling materials. So not only putting in mind the environmental aspect of it, but also thinking about the communities that have low incomes or low resources, which is also something we don't see that much in like innovative technological or structural systems. So I think that was very interesting.
Well, thank you. Yes, no, I think it's as I showed you the first example, right, done with cartoon, meat cartons. I'm trying to be to show the versatility of the system. Of course, has limitations, has everything else, but the idea is to kind of showcase that a very primitive system. One of the most primitive construction systems is Adobe construction, right? So if you give it like a little bit of an update with today's technologies, like high-end concrete, but also 3D printers or even recycle, can be like a hybrid, right? Can be using really low technologies recyclable materials like bricks or containers, or it could be more high end, right? It really depends on the project. But yeah, I would love to do a project like this in a local, community that using local resources. That would be my dream, to do something like this so to showcase and to test it, see if it works, and then understand the limitations and understand the potential, right? But one thing I think very important to mention is, as Pablo mentioned earlier, is the idea of these are structural components. It's not just a cladding. So it's really resolving the structure, the envelope, and the envelope means, it's watertight, airtight, humidity tight, and temperature tight, right? So it's really trying to propose a system that tries to resolve as much as possible. By the way, one more thing, the thermal mass is definitely a benefit. You can also include insulation to make it even more efficient, like 1 or 2 inches of foam. I didn't do that, but I know it's very common in the precast industry. So my goal is to do a couple of those tests too, like with insulation, to potentially do some thermal analysis, and then see how it works.
And then so you're adding an additive to the concrete to make it impermeable.
But the concrete that I'm using already is, as I mentioned, is with a high performance, is much denser and compacted than traditional concrete. So it's taking care of.
Yeah. So the capillarity is not exactly. That the water does not go through the capillary.
Exactly. So the water does not penetrate the material. Now let me tell you something. I'm very familiar with precast construction in traditional concrete. The standard is, when they do walls, is typically a standard wall out of precast is 4 inches of concrete, 2 inches of foam, and 3 inches of concrete on the outside. What they say is beyond 2.5 inches of concrete, I'm talking about regular concrete, not ultra high performance. You don't need any type of water treatment. I mean, the concrete is already taken care of. Even traditional concrete can take care of that. I don't know if that's 100% truth, but the
problem is I know that, but the problem is humidity. If you live like for instance in a basement, you feel the humidity. Like water does not go through, but the humidity does. Like it feels damp. But I think in the high density concrete, I'm not sure if you feel damp or not.
I don't know either. Now you can also add a vapor barrier into the foam. If you use foam, you can actually add a vapor barrier, so that way it will take care of the vapor. So again, it can be done, but yeah, I haven't done it, but it's possible.
All right. Okay, thank you, Pablo, so much for your presentation. Very interesting work, and I hope that you take the prototype and you make it work as far as you can, and that you continue modifying. I think it's terrific and very interesting what you're doing. So thank you for your lecture.
Yeah. No, thank you so much. I'm happy that you guys enjoyed it, and yeah, I think it's a good opportunity to share my work, and I appreciate your words, Pablo. Yes, I'm hoping to do some real prototypes. I mean, larger scale projects. I'm applying to a couple grants. Yeah, so we'll see what's next.
All right.
Okay. Well, thank you everybody for watching this, and I hope to see you